How do you pronounce your last name?
Sorry?
How do you pronounce your last name?
Bhattad.
Bhattad. Okay.
Yeah, that's
Alright.
great.
Okay, I think we can get started. First of all, thanks for coming during spring break. So it's my great pleasure to introduce our speaker today, Anand Bhattad. So Anand right now is research assistant professor at TDIC. Previously, he got a PhD from UIUC with theory for science. So Anand is working on a very exciting area at the intersection of computer graphics and computer vision, primarily focusing on understanding the knowledge encoded in visual generative models, right?
Yeah.
And his previous work has got best paper nomination at CPR 2022. And he's going to talk about what generative visual models understand and don't understand about physical world today. So please welcome Anand.
Right. Thank you. Thank you so much. Thank you for a very kind introduction, Tianmin. It is a great pleasure for me to be here today and discuss my research on understanding generative visual models. Okay. It is, as we can see, it's an incredibly exciting time in computer vision. Today, we have very powerful generative models that can produce videos that seem to capture the visual world. So consider the scene generated from OpenAI Sora. Uh, The scene was generated using a simple text prompt that we see on the left of the screen. So it says a graduate student walks down the GHU campus with her friends in Baltimore. She wears a hoodie with the GHU logo and carries a backpack. She walks confidently, and the street is damp and reflective, creating a mirror effect. As you can see that most of the pedestrians or people that are walking, they seem to be arranged in very realistically. The overall, sorry?
So that's not all campus.
Sure. That's the models understand, or the future campus maybe that we'll see in few years. The overall arrangement looks quite realistic. The spatial cues, the camera motion looks fluid. And if you also look at the reflections, they are quite realistic. It seems like we have unlocked a superpower, turning language into world models. But if we go deeper and try to understand these models more carefully, let's watch this second video. First, let me show you the prompt. So in here, we have two balls, a soccer ball and a tennis ball. They will be dropped from the same height. We have no air resistance. It's a gymnasium. And we want to capture the motion of the ball as they hit the ground at the same time. As you can see, this is a test of gravity. Now, let's see what the model produces. Okay, so if you saw, the soccer ball miraculously turns into a tennis ball at first. The contact points are off. You would notice that the tennis ball suddenly gains acceleration out of nowhere, right? And also, if you pay attention, the soccer ball, the pentagon on the soccer ball morphs into a rhombus, the second soccer ball. If you let me play it for one more time. Observe the tennis ball. First, it will gain acceleration suddenly. Look at that now. Now you also see the pentagon. So it is unclear if these models are understanding anything about the visual physical relationship, or they are just operating as mere pixel parrots, something that they have learned from billions of training images and trying to come up with a mixture of or assemble pixel parts from various training resources and produce these outputs. At individual frame level, they look stunning, they look quite impressive. But if you look at the whole sequence, then the obvious physics failures become obvious, or the object permanence failure become obvious. Even if you look at, let's say, a single image, this image looks quite realistic, right? Can anyone tell what might be going wrong in this image? Yes. Exactly. So if you pay attention, if you look at this, so people are holding hands, in the couple are holding hands, but in the shadow there is no contact point, right? So some of these failures may not be obvious to naive observer, but if we look at these images more carefully, we would see that there are this failure modes. So my research goal is to build generative world models that are faithful and understand the physical world. And to do so, my research follows a three-step process. First, I probe or study the knowledge that these models have acquired, the physical knowledge that these models have learned. Then I systematically analyze and try to find their failure modes at scale. and come up with the shortcomings. And then finally, I use both this knowledge to come up with a improved way, improving these models in a faithful manner. Even though I show this in a sequential manner, in fact, this is actually a cyclic process. This probing, analyzing, and improving is a cyclic process. It diverges from conventional focus on just scale up with more data and scale up the more model size. It reflects a rigorous scientific pursuit to build better models by deeply understanding their strengths and weaknesses. So here is what we'll cover today. First, I'll explain I'll go through one of our interesting findings of what these models know, a surprising discovery. Next, I'll talk about what this model should have known, but surprisingly don't. And I'll show that there are perceptual failures that we can detect them at scale. And then I'll briefly talk about one way of improving generative models, in particular, overall 3D awareness. And finally, I'll talk about what's the way forward. So let's start with what generative models know. Again, let's start with a simple example. Here is the prompt and the image. So we have a living room with sunlight streaming through windows, and this was generated by DALL-E 3. But let's try to see what's happening in the scene. First, at the very high level, the overall object shapes look quite realistic. The sofa is of the right shape. The table seems appropriate size. The plants at the corner, they all look reasonable. The spatial composition looks correct. The carpet is below the table. The sofa is near about the edges of the room. The plants are on the edges, and the light is coming from the window. So it seems like the model has a good grasp of the scene geometry, the different materials, like the light seems quite, the reflection of light seems quite realistic. For example, if you look at the cushion, you see a strong reflection over there, and the light is coming from the window. So the model seems to understand at a very high level how images generally we see, the real images. Now the question is, what kind of representation these models are learning? Are they something like pixel parrots, reassembling parts of the pieces from the training data and then just spitting it out? Or maybe they are doing some complex abstract matching, reminiscent of, let's say, old classical Mondrian, Kandinsky, or some features which we don't really understand. Or the other alternative is maybe these representations are actually physically grounded, something that is related to surface material, lighting, and so on. What is it? Before we answer this question, let's try to take a step back and understand how images are formed. We know that images are 2D projections of the 3D world. So this is a very simple setup. There are 4 objects, a cyan cone, red cylinder, a yellow sphere, and then another sphere. Now imagine we are going to have a camera here, and we are going to take a snapshot. Let's say we have a spotlight that is going to cast light on this. Now, if we take a snapshot of this image, what we see is a grid of 2D RGB pixels. But what we actually perceive is the 3D shape, the overall appearance and arrangement in space. Now, what I just showed you is a sophisticated process going from a complex 3D setup into a simple 2D image. It's called rendering in computer graphics. And if we abstract this, what we started with was some material, lighting, camera, and geometry. We call it scene parameters. And then we render it to get the RGB image or the image that we see. Now, one of the goals in computer vision is to inverse this process. Given an RGB image, we want to inverse this to recover the scene parameters, material, lighting, camera, and geometry. As you can see, this can be ill-posed or even a hard problem or difficult problem, because only from a single image, most of the things are hard to recover. Things may be occluded, may not be visible, or the light source may not be visible. So it's hard to recover just given from a single image. So in 1978, Barrow and Tenenbaum came up with a concept called intrinsic images, which is a 2D approximation of this 3D scene parameters. So they said that instead of measuring materials, let's measure something called albedo that is completely light independent. What we see here is the actual color. We can clearly see the red cylinders, cyan cone, and the yellow sphere. All the light independent effects, the actual color is modeled in albedo. Then we have something called shading that captures all light dependent effects, the shadows, the interreflection, the reflections, or glossy surfaces. Anything that is related to lighting is modeled in the shading. Now, instead of measuring where the camera is, we measured something called depth maps. Depth is where for every pixel, we want to measure how far they are from the camera. So the way to interpret this is darker color means here closer to the camera, lighter color means they are farther away from the camera. And then instead of measuring the full geometry, we measure something called surface curvature or surface normal, where here the red color means it's a float pointing towards upward. The blue color means it's pointing towards the camera and so on. So this intrinsic images, if we look at them all together, so we have 4 parts or 4 factorization. One is light independent, that's albedo. We see the actual color. The other is all light dependent effects called shading, where we see all the shadows, interreflections, all light dependent effects. And then there are 2 somewhat geometry related. One is surface curvature or surface normal, and then the depth maps. Now, why these intrinsic images are useful? If we inverse this process, like if we take all these intrinsic components, put them together, and then we can get the same scene back, the rendered scene. Now, what this makes this interesting is that if we just manipulate one of the component, let's say if I change the shading, I get a same scene, but with different lighting condition. What just happened was light source moved from right side to the left side of the scene. So if we have to compare both this scene, you would see that the shadow has moved from the right side to the left side. Just by manipulating one of the factors like shading, we are able to generate different scenes, manipulate it or edit it, and get a different version of the same scene. Now, as we saw, these are some of the fundamental properties that is important for image formation. What if generative models are actually operating on these intrinsic images? If they do, can we recover them? And it turns out, yes, we can recover this intrinsic properties from the internals of models. And at the time when we did this research, StyleGAN was still the latest, greatest state-of-the-art model of that time. So just to give you a quick overview of how StyleGAN works, in StyleGAN, you sample from a Gaussian distribution and send it through a series of MLP layers or mapping network to give you style code. The style code is a 512 dimension embedding. Now we have a generator with series of up convolution layers. And this style code is injected to all these layers to give us a generated image. If we draw different samples, we get different images. Now, what is interesting about this StyleGAN is that this style code turns out it learns some disentangled representation of images. So what do I mean by it? So if we, let's say this 512 dimension code, if we project it in 2-dimensional plane, then this gray dot represents the image that we are going to generate. And if we move in one of the direction in this style code space, we may see that the room size increases or decreases. If we move in other side, we may observe that the camera position changes and we get like a nice 3D layout of the scene. Or if we move in another particular direction, we may also see that a bedroom may morph into a living room. So this kind of property naturally emerges inside this style code, this just 512 dimension code, which you can manipulate to get different versions of the same scene, or you can manipulate this scene. Now, what if we can use similar procedure to recover the fundamental intrinsic concepts that I described earlier? So what we want to do is, this is the same schematic I showed you earlier of StyleGAN. Now, instead of editing images or finding this control, we want to find what offset that we need to apply to the style code that gives us intrinsic properties. Like, let's say if I apply this direction 1 of 512 dimension size on top of the style code, I get something like, let's call it normal. So it's 1. If I apply another direction like orange, we get depth maps. We can also find like offsets for segmenting lamps, beds, and so on, or albedo and shading. And now the way to find this offsets is using a pre-trained model that gives us all these intrinsic maps like surface normal, depth maps, lamp segments, albedo, and shading. And then we can apply a loss like simple regression loss only to update these offsets. One thing to note here is that the generative model is pre-trained and frozen. The intrinsic image predictors are pre-trained and frozen. We are only going to update those 512 dimension offsets, 5 different offsets that we care about. The rest of the model is completely frozen. And what we find is that if we have few hundred images, that is good enough to recover this intrinsic properties that live inside this style space or the style codes of this model. One thing to note here is that the model has never seen this kind of images during training. This normal depth, they are completely different than the actual images that we see. So it is quite surprising that just by manipulating this 512 dimension offset, we can recover something far more fundamental physical concepts that are important for image formation. So if I look at some results, here is another image generated from StyleGAN. And here what I'm showing you are normals, depth, albedo, shading, and lamp segments. Now let's compare with state-of-the-art models of that time. These are customized, supervised model trained with millions of images, if not billions. And the numbers that you see at the bottom in red, these are number of parameters that were required to train this model. So all of these models require at least 100 million parameters. The segmentation model require 1 billion parameters. And what I just showed you in previous slide is that we are just manipulating 5 12-dimension code to recover this all these intrinsic concepts. One thing that may be apparent looking at the images is that we are able to segment all the lamp segments in the top. If you see at the right corner, all the 3 lamps that you see are segmented, whereas a 1 billion parameter model trained with millions of images is unable to segment the lamp. One hypothesis is that since the model has generated these images, it must know where these lamps are. So that's why we are able to pull this out information. And even if you look at some of the surface details at the lamps, you would notice that some of the details are well preserved as compared to the bottom. Overall, these results are highly comparable with state-of-the-art models by just using few labeled images and manipulating a 5 12-dimension code. I want to pause here for a moment and emphasize that this was the first work to demonstrate generative models are learning underlying physical concepts without using any explicit supervision. And it is quite startling how things have progressed in computer vision so far. In 22-23, when we did this research, like the camp was divided, half of the people didn't believe that this was possible. And half of the people thought that this is so obvious, why are we even solving this problem? But we all know today that the best way to recover some of the fundamental concepts is to fine-tune this model, generative models, and this is like a common knowledge. Now, the interesting question next is there anything special about StyleGAN? What about other models that are state-of-the-art today? And it turns out in our follow-up work, we found that it really doesn't matter what generative model we use. It could be an autoregressive model, and we can still recover intrinsic images of it. It can be a StyleGAN model trained on completely different image distribution, just faces, we can still recover it. Or we can have a improved version of StyleGAN model, we can still recover intrinsic images out of it. And even the latest, greatest stable diffusion models, we can use similar probing method that I talked in previous slide. We can use this same method to recover intrinsic images from all of this model. So the main takeaway is that generative models of all types, irrespective of the training type, autoregressive, GAN, or diffusion, know something about intrinsic images, and we can easily recover them. Another interesting observation that we made was, as models improve, the quality of recovered intrinsic images also improve. Here we are comparing with 3 different versions of stable diffusion on x-axis. These are 1.1, 1.2, 1.5. They have same number of model parameters, mostly trained with similar number of images, but with better training protocol. And we know that the visual quality improves. On the y-axis, we are comparing the angular error or the surface normal error. As you would see that there is a trend. As models are improving, we are able to recover better intrinsic images. And the state-of-the-art on is about 18.9 angular error, and we are about somewhere about 20.5. And as models improve, it seems like we are going to see better and better. With few labeled images, we can get performance as good as state-of-the-art model that are trained with billions of labeled images and billions of separate model number of parameters. Any question at this point before we move on? Yes. Okay, can you repeat the question? So if I understand your question correctly, we are using a separate network to find this offset. Is that right? Yes, that's a very good question. In fact, yes, we are using a separate network to find this offset because we are looking for certain concepts, and the separate network is only acting like a guidance mechanism. It is helping us to look for those concepts inside this model, but we are not updating the other model that we are using to recover these concepts. You can see this as, let's say if we don't have access to actual ground truth, we can use some model that gives us pseudo ground truth where we can use this concept. And the other important thing to note is that we are not updating the generative model itself. We are only trying to find this offset, 5 12-dimension offset, that's it. And that is good enough to recover this properties. So we are not doing any learning as such. We are just optimizing for finding those offsets. So what this is showing is that this property is already emerged somewhere inside this 512 dimension code. We are using this guidance mechanism to find those where these properties are. Yes.
So given that you're using this off-the-shelf network,
Right.
This off-the-shelf network is creating this some supervision.
Right.
We are imitating, you're getting some signal from this off-the-shelf network. I'm trying to reconcile this with your claim that you're not using explicit supervision, but by proxy of using this off-the-shelf network, aren't we using explicit supervision?
We are not using direct supervision. We could use some labeled images if we had access to ground truth, but most of these decompositions are ill-posed and it's hard to recover. Like normals and depth, you can get it from synthetic data set, but light dependent and light dependent independent components is very ambiguous. So that's why we use off-the-shelf model. But if you have access to, let's say, actual ground truth images, you can use them. But what is more important here is that we need only few hundred images. That's it. We don't need billions of, and we are not distilling the model. We are not updating the model itself. We are not distilling the knowledge from model. We are just trying to find the offsets that is good enough to find this concept.
Did you say a few hundred for training these off-the-shelf networks, or for your somewhere else in the model?
Few hundred only to update this 5 offsets.
But shouldn't we also take into account the supervision that we had to utilize for training those off-the-shelf networks?
Sure, if you have, that's a very good point, and I agree with you that we are using some knowledge of previous off-the-shelf model, but let's say we have access to, someone gave me access to 100 images ground truth labeled example, that is still going to be good enough to find this problem. So what I'm showing you is that this properties already exist somewhere inside the model. We are using that model's knowledge only to find it.
But given that we need this additional source of supervision,
Sure.
how do you reconcile this with saying that the representation already exists? As in,
that's a very good point. I'll get to it in next few slides. How do we know if this model is actually making use of this representation or not without any explicit supervision? I'll come to that in 3 to 4 slides. Okay, right. All right. Yes.
Curious that, for example, like texture, it's also important to ask, and with like the predefined features, so those like consistently like texture within the predefined feature. Like,
Can you repeat that?
for example, like texture, because you define, for example, that segment of window.
Right.
Some of the features may be not included in this category table.
That's a very good question. We do this analysis in our paper where we show that, is this a generic regression machine? Whatever the output is, they may be structured or unstructured, can we still recover them? And it turns out we cannot. One example that we do in our paper is that, let's say if I cut image into 2 parts and flip them, can we find an offset that is able to find this operation? And it turns out we cannot, because those are not structurally how images are formed. So those are not innate properties of image formation. So that's why it is hard to recover those it's a simple operation. Just I cut image into 2 and flip them. Those kind of simple operations we cannot find those kind of controls inside this model because those are not fundamentally required for image formation. So what this is showing is that anything that is fundamental to image formation emerges naturally inside this model. And this is kind of a way to show that how to recover them. Irrespective of their pre-training type, irrespective of their model size, model type, if the model has learned to generate good quality images, this property naturally emerges. Okay, so we had some interesting question. How do we know this model is making use of this information? One thing which we could do is, I showed you that if we manipulate one of the component, then we could get relight of the same scene. And in fact, we do that. And we find that just manipulating one of the component, we are able to get image relighting without using any label data set. If you look at this video, most of the changes that you see is mainly due to lighting. The bedside lamps are switching on or switching off. The overall scene geometry does not change. The spatial layout remains preserved. So here, this shows that just by manipulating one of this component, we are able to observe the phenomena that we are looking. So this means that this model is using this information in order to produce this output. So this is one of the implication that we can get relighting without using any label data. And this is Very difficult problem. Why? Because the model must understand on its own where the light sources are. There is no label. It must identify that there are two lamps and there might be a window which is not visible. Second, the model must also understand how light interacts with different surfaces. The light is going to behave differently when it hits the carpet. It's going to behave differently when it hits the table and so on. And the model must understand different light surface interaction. And finally, in order to see second order effects like shadows, reflection, and everything, the model must also have an understanding of the overall spatial layout of the scene, what is being occluded and what is not. And it is quite surprising that these models are able to do so. But one of the limitation is that still, whatever I'm showing you, these are implicit control. We don't have explicit handle over it. Like if I want to say, turn on the lamp, we cannot. I mean, we just look for probe and I'm just showing you over here. So this is one of the big limitations, that these are mostly implicit control. Another interesting implication of this work is that because we know that intrinsic properties emerges inside this model, and like we were discussing, this light dependent and light independent effects are ambiguous and it's hard to decompose them. Can we improve this phenomena? So current challenge that we have is this: the albedo shading decomposition is very noisy and inaccurate. A research question is, can we leverage this rich prior knowledge of these generative models to recover an improved representation? So concretely, we want to learn to factorize light independent and light dependent components as latent variables. Why for 40 years, we have always treated this light dependent and light independent components like image-like maps. But why do they have to be image-like maps? Why can't they be latent representation if they are able to better decompose light independent and light dependent effects? So we solve this problem from that perspective, and we use this intrinsic representation as latent variables. What do I mean by it? Given two scenes, same scene under two different lighting conditions, we are going to train a simple shallow network that is going to factorize this image into two components. One, a low dimensional lighting like vector. It's just a 16-dimensional vector. And another, we call it intrinsic feature. We are going to do the same thing with the other image from the same network. So they are going to share parameters. Now, what we are going to do is we are going to decode light vectors from the first image and the intrinsic feature map from the second image to give us an image. As we are trying to have lighting from the top image, this image should look like the top image. Exactly. The resulting image should appear as good as the top image. We enforce another law, we ask that the model should generate features for both these images to be similar to each other. What we are trying to do is we are trying to factor light independent components out. So irrespective of these two images, this feature stack should be the same with each other. Now, if we do that, after we train this, we can get good relighting, which that's not that interesting. But let's say if I cut this connection out, if I remove the lighting component out of it, what do we expect to see from the model? It turns out it surprisingly produces light independent effects from the model. So it is generating an image that is completely suppressing light dependent effects. More concretely, if you look at these two images, here in the first image, you can see that there is a mirror and there is a light surrounding it. In the second image, it's an open refrigerator. Now, if we use this, in the generated images that you see, all the light dependent effects are suppressed. Most of the light dependence effects are suppressed. Now we can clearly see what is inside the refrigerator. We can see that there is a red ketchup bottle on the side. If we compare with the previous state-of-the-art model trained with, again, millions of training images with millions of training parameters, they are still unable to suppress light-dependent effects. Now, one more thing that we could do is we could replace this simple generative model that we were training with using a more powerful generative model like Stable Diffusion. And if we do that, one of the main problems that we had was we did not have explicit control over lighting. Now we do. We can have an explicit control over lighting. We can transfer light from one image to another in abstract sense. What do I mean by it? Let's say if I have two images, I want to abstract lighting from the first image and apply it to the second image. So let's try to understand what's happening in this scene. In the first image, most of the light is coming from the window. And in the second image, the dominant light source is coming from the lamp that is on the ceiling. Now, in order to transfer light from one image to another, what must happen is that this light source must be turned off, and most of the light should be coming from the window. And if we use this same approach that I talked about, here is what we get. You can see that the lamp source is turned off. And you can see that most of the lighting is coming from the window. You can see there is a nice reflection over here on the table. There is a strong light coming from the other side of the window that is not clearly visible. This provides us one way to explicitly control lighting by abstracting lighting from one image and transferring it to another. So to summarize, so far, what I've shown you that generative models know something about intrinsic images, and these are fundamental physical properties. An interesting finding that we saw was as models improve, the recovered intrinsic images improves. This allows for interesting applications like doing relighting with labeled data. We can get improved albedo and also get some sort of explicit lighting control out of it. Any question at this point? Yes, Dan.
Okay, so you can control lighting, which I can see how it can work because it's independent of the content of the image.
Which one? Sorry.
It's independent of the physical structure, the content of the image. The lighting can work because you don't change the content of the image.
That's right. We don't want to change content.
Right. So, but then you also have other kind of intrinsic of properties that you can control other.
Right. That's a very good question. And we can do it where, let's say, if we want to preserve lighting but change other things, we just need to swap the order. And what we find is that the overall lighting remains preserved and the material can change, like object material changes or color changes and so on. Anything that is light independent can change. You can just swap the order, the way we manipulate it.
But I guess not depth.
Not depth, that's right. We can right now the same scene, we want to preserve the scene layout and structure so that the depth has to be preserved. So we can't change the depth. But there can be, you can imagine, I'll show in next few slides where we can control the camera as well and get some sort of different depth estimation out of it. Any other question? So there are some data set where we are collected in a careful laboratory setup for lighting setup. So each scene are captured in 25 different lighting conditions. So you have a ground truth for it and they're calibrated. I didn't get into those parts in the interest of time, but those analyses are in our paper where you can compare with the actual ground truth. And then you can also do this human evaluation if what we are getting is correct or not. All right. Now, let me switch gear and talk about bad stuff. Okay. What generative models should have known, but surprisingly don't. So here are two images that similar to that I showed earlier. In both these images, if we look at this carefully, in the first image, the shadow of this person is disjointed from the person that you see. In the second image, the shadow of the coffee table does not match the cubic shape. Now let's try a hard example. So here are two images. Which of the two do you think is real, left or right? And why? Any guesses? Yes. Left image is real, right image. Okay, let's hold on for a minute and let's see. Before we answer this question, let's take a small detour and try to look at this images from a different perspective. There's something called perspective projection in computer vision, where we know that images are like we know 2D projections of 3D world. So the parallel lines in 3D, they meet at a point or converge at a point called vanishing point. And these lines are called vanishing lines. And the horizontal line that you will see through this vanishing point is called horizon. Now, this perspective projection has been used in various different applications in computer vision. Let's say if I know the reference height of this teleport booth, I can, using that information, I can approximate the height of the person standing next to it. Or if I know where this vanishing points, I can adjust the depth of field focus of my camera and take a snapshot, let's say more focusing towards the front of the camera. Or we could create nice illusion out of it. Now, we can use the same idea to find which of those two images was real. So if we draw lines, at first they seem to meet at a vanishing point, parallel lines. But if we draw more lines, then it becomes obvious that the left side was real and the right side was generated. You have a great eye. So yes, the left is real and the right side is generated. Now, the images that I showed you earlier, they also have this perspective errors. If you look at it, they seem to meet at a point. Now, if we draw more lines, then we see that there are multiple vanishing points. Even though here the degree of error seems very small, I'll show that this is quite significant to detect these images at scale. So far, we have made observation that, okay, there are shadow and perspective error in generated images, but I can't be looking at every single image to draw these lines manually or look at if there is a shadow disjointed from the person. Now, question is, can we derive this hues at scale? If you are able to do so, then we can simply train a model to distinguish whether an image is real or generated. Question.
Isn't that what the discriminator in the GAN is already supposed to be? Or are you just trying to improve the discriminator?
That's a very good question. And we thought so, but turns out there are certain type of interaction. These are long scale interaction within images. Like most of the time, the light source is not visible. Most of the time, the lines may be going through top right corner of an image to bottom left corner of an image. And there is nothing and these are very subtle cues. So the discriminator is, you can fool the discriminator easily by getting local textures right. And this global phenomena can easily bypass it. And then the second issue is there is nothing in our network architecture that encourages this long range phenomena to behave.
Yes, you're saying that this is a failure of current discriminators. If you fix it, is the right thing to do to put it back into the GAN?
We'll talk about it in next few slides. Yeah, but that's a good question to have. Yeah. All right. So can we derive these cues at scale so that we can train a classifier? And yes, we can use some of these cues that are already available. So we found two such cues. One is off-the-shelf pre-trained object shadow detector. So you can use a state-of-the-art object shadow detector and generate object mask and shadow mask corresponding to it. Then we can train a simple classifier to tell whether it is real or generated using a population of real and generated images. One thing to note here is that we are only going to see object mask and shadow mask. We are not even going to see the raw RGB pixels. Just the derived geometry cues is what we are going to operate on, and we will train a simple classifier whether it is real or generated. And once we train this model, if you look at the activation and using standard GradCam procedure, what we find is that the model is, when making predictions, doing the right kind of job. For example, if you recall, the pedestrian shadow was disjointed. So the red means that there is a high error, blue means there is almost no error. So most of the error is coming from that pedestrian. In the second image, the shadow of this coffee table was imperfect. So most of the error is coming from the shadow of the coffee table. Now for perspective error, we use a model that gives us something called perspective field. So perspective field, the way to think about it is that for every pixel in an image, we have a gravity vector or up vector, like the orientation from the actual gravity. And then we also have something called latitude map, where this latitude map is basically the orientation of every pixel from the horizon, the flat line that we saw. So it's a polar coordinate. So we have the sine coordinate and then a cosine coordinate. So these are two, and then there is a gravity vector. So these are basically a 3-channel output. So this gives you some cue about perspectives. And again, we can train a simple classifier only on this perspective field map to tell whether an image is real or generated. After we train it, again, if you look at the GradCam errors, it turns out mostly the model is looking at the edges. That's where we tend to draw lines in order to see whether they meet at vanishing points. And we evaluate this model at scale, like over 6 state-of-the-art generative models, open source, closed source, over 1 million indoor images for each and 500,000 outdoor images. And what we find is that it is very easy to detect whether an image is real or generated using only this derived geometry cues. Here, this is a area under ROC curve. On x-axis is a false positive rate, and on y-axis is a true positive rate. If you use just object shadow cues, we get about 82% of the times whether an image is real or generated. But if you use perspective cues, we get about almost 99%. Even though the degree of error was small, 99% of the times we can tell whether an image is real or generated only by looking at perspective cues. I must also say that it is not that difficult to tell whether an image is real or generated by looking at other cues. You can simply train a ResNet classifier directly looking at image pixels. You can also train some signal-based classifier using Fourier transformation, and you can still tell whether an image is real or. What gets interesting is that when those classifiers cannot tell whether an image is real or generated, we call this hard test set. This derived geometry cues are still very reliable. Object shadow is just above the charm. It's not That's significant 61% of the time. But if you look at the perspective cues, it is on those hard examples, we are still able to tell whether an image is real or generated almost 84% of the time. Here are two interesting examples that I love to show. Again, there is no trick question, both are generated images. But can you tell why do you think these images are generated? Okay, let's not play the mystery game. I'll quickly tell why these images are generated.
Too little texture.
Sorry?
Too little. They look too clean.
Oh yeah, that is, yes, if we are not looking for texture cues though, but if I agree with you, if you look at texture cues, then we can tell whether an image is real or generated, but we are operating mostly from perspectives and shadows. Yeah. So in the first image, the reflection of the shadow that we see of the woman is quite real. So the object shadow model thinks that the image is real. But in the bottom image, if the image has to be real, it has to come from a planet where there are at least two suns for each of the suns. So if you look at it, the shadow is pointing in two different directions, right? Whereas in the first image, there are perspective errors, like there are multiple vanishing points. So a perspective field model is correctly classifies that the image is generated. Whereas in the bottom, there is not enough cue. There is only a horizon. So the perspective field model thinks that this image is real. The purpose of showing these images is that there are complementary signals that both of these cues can be used to detect whether an image is real or generated or not. Even if, let's say, magically this problem goes away in Stable Diffusion 6 or 7, but we can still rely on this complementary signal to detect whether an image is generated or not. So the main point is generative model, even today, don't know projective geometry. When we wrote this paper, we had this ... for now. It's so easy to find this problem, but it turns out it is very, very difficult to fix. It's indeed very hard to fix this problem. Like coming back to this question, can we use this as a discriminator and improve the model? And it turns out we can improve maybe 5% of the images, but not. The error is still significant, and it is very, very hard problem to fix. And the reason is these are long range effects, and there is nothing in our network architecture that encourages long range interaction.
So you're saying the generator has a complementary.
Generator has a, yes, sir. Okay. To summarize what we saw so far, generative models have the shadow and perspective errors, and we can detect them at scale to tell whether an image is real or generated. And I do see this as a good feature to have rather than a bug, because it's not so obvious to naive observers. So it might be a good thing to have for detecting fake content. But at the same time, it also shows that there's a lot to do in order to fix this problem. Now, let me briefly talk about how we could improve this model. More specifically, we are interested in improving the 3D awareness in this model. What do I mean by 3D awareness in this model? Oh, I didn't see. Okay. Let's see if I can. I was looking only at those screens. I didn't realize. Okay. So how do we, what's the problem with this model? If you look at state-of-the-art models, when we try to move the camera around, we get most of the details are missing. The background completely gets washed out and everything. So there is some problem in this model to understand about 3D awareness. So when we analyze these models more carefully, and when we found out that most of these models were trained on images or videos that were scaled from something that looked like this. But if you think about it, the world we live in is 360, right? In order to improve, in a way, 3D awareness inside this model, we need to have data set where there are some rich 3D signals. So the main contribution of this work is that we curate high quality 361 million videos and then fine tune our model using this data set. And here is a sample of how our data set looks like. So at any point, you can take 360 snapshot of the video. Here is another example of a trail. So at any point, we have access to the 360 capture from 360. And the way to train.
By driving around with an omnidirectional camera?
Right. So you can have a 360 camera and everything. And we don't have to do it. People have already done it and they've put it online. We just have to state it. And the way to train this model is train a simple conditional image generator model where we given a starting input frame and some camera transformation between the two, and there is a noisy target that we can start with, and then train a latent diffusion model to get the target. So just we are going to predict one image at a time. That's it. Given a camera transformation, what is the next image? After we do it, what we found is that we can sequentially generate many images from the previous output. And way to check these images are 3D consistent is we just put them into, let's say, a standard 3D reconstruction pipeline, which we have built for 20 plus years, like structure from motion or code map. We do see that there is a nice 3D structure that emerges from only using this image queues. We can also figure out where the cameras likely are, and using that also gives us another signal if our camera transformation makes sense or not. Here is another example. This orange curve shows the camera trajectory. I can see that there is a nice 3D scene layout that seems to emerge from this model by using just camera from control. I want you to pay attention to this couple of frames. In the first image, notice that the light source is not visible. In this frame, you would see that there is a light piercing through the building. This is a light flare, which is quite plausible, which is quite realistic. The second thing to notice that the drainage was not visible in the original frame. Now you would see that there is a drainage added to it. If you look at from other views, you would see that there are cars added that were not visible in the original view. There is a stop sign, fine grain stop sign added, and there is a lamp pole that is added. And if we put them in this nice 3D reconstruction, we see that there is a nice 3D scene layout. And if we compare with previous method that I showed earlier, we find that it preserves the details. It's not perfect, but it has better 3D awareness, and it is able to preserve most of the details right. But how do we quantitatively compare at scale? Because we don't have, these are generated outcome. We don't have access to ground truth. What we do is we generate multiple images, overlapping images, shooting by camera. And then we can generate what the images look like from different methods. You can see the previous method, there are details missing. In our method, you can see that a new painting was added. There's a new cabinet added. Now, what we could do is we can look at overlapping regions and see how similar they are from the original view that is visible. And then we can quantify if they are realistic or not using the standard metrics like perceptual similarity or pixel to signal noise ratio. In fact, if we improve 3D awareness in generative models, what we find is that we could also improve the projective geometry in generative model. This is an ongoing work. These are preliminary results. The previous model that you see is on the left. And once we have 3D aware losses or improve 3D awareness in the model, it seems like we are getting models that are well behaved. Okay. Now, let me talk about what's next. So far, what we have discussed is that this model seems to understand what I like to call this as intrinsic physics knowledge, as in something, these are fundamental properties that are required for image formation, and we are able to, they seem to understand this, and we are able to recover them. Next, I believe we need to focus more on intuitive physics aspects of this generative model. If they understand anything about what the support structure look like, what is dependent on what, and eventually we will have to deal with actual physical knowledge if we really want to deploy this model in our real world, if they understand anything about gravity. If you are able to do so, I do see that there are going to be enormous application in robotics and beyond, scientific discovery and others. And we may also be able to find some hidden representations in this model that vision science is yet to discover. Let me go slightly deeper into one of this and talk about it. Let's talk about intuitive physics for a bit. Yes.
And assume that once you have probably that subnormal or depth, and then you probably can generate policy or videos. But what you don't have a model generate those intrinsics.
We don't have a good model to generate those?
Yes, because you are assuming that your kind of video, generative videos are based on a good quality of intrinsics. I think it's very hard to scale up the model that can generate intrinsic signals. That's what is normal for.
But we do have today models that can generate high quality depth surface normals. And we can use those models to see if this model has this understanding of it.
Yeah, so how do you evaluate that you have?
That's a good question. So we do evaluate on real images where people have captured with actual sensors, where we can estimate the depth map with LiDAR sensors and everything, and then we also have surface normal. We do evaluate on real images, but for albedo shading, it's very difficult because we don't have those kind of sensors where we can easily extract light dependent and light independent. So we have to rely on synthetic data for this. So we evaluate for those things on generated from, let's say, computer graphics. You can generate using Blender or Unity, and then you can evaluate on synthetic data set. I know that's not good enough, but that is something to begin with. But
why don't you just use some kind of really algorithm to compose the image?
that's a very good question. But the problem with most of this rendering algorithm is they come up with some or other assumption. And then those are not really reflected in the real world phenomena. You have to make some or other assumption when you're doing this rendering like Blender, Unity or graphics. They make some or other assumption. Then those are not necessarily reflective of how the real world behaves. But it's good to have. We do evaluate on those synthetic images from generated images. But my point is that's not just enough. We need to think beyond. So that's why we also do human evaluation studies.
Yes.
If those metrics make sense or not. So we need like a comprehensive evaluation, synthetic data set, some real world data set where we can capture using sensor data, and then also the third thing is human evaluation.
Yeah, I'm generally, but if you just use the intrinsic as an action, and then to redesign your training model, will not touch the basis of what's rendered.
That's right. I agree with you. Yeah. All right, great point. Okay, so we are interested in identifying object dependency and support relation. We want to know which objects is dependent on what. One way to think about this problem is we can ask generative model to generate images. What would the picture look like if I remove one object at a time? So for this, we are proposing a new task called visual Jenga. It's like playing Jenga with images where you want to remove one object at a time until the stability of the scene is preserved, overall physical stability of the scene is preserved. So the goal is sequentially remove one object at a time until we are left with the background. If we are able to do so, it will help us probe support relation and object dependency. And it may help us understand the structural knowledge that is hidden inside this model. Let me quickly show a simple algorithm that we developed first. And here are some results. This is Elisha's office. You can see there are a lot of objects. Books on the table. You will see that objects on the table are cleared first, then the table. Books before the bookshelf. Sorry for the blotchiness. Okay. So, yes.
Why are the only objects that disappear inside the office and not outside the window?
Because that's the limitation of our approach. I'll not go into the entire detail of how we do it, but something that is easily detectable is what we remove. But those things are kind of farther away, so we can't see them, so we can't detect them, and we can't remove. But that's yes, fair point. So how do we solve this problem? By making a simple observation on how images are, how visual world usually appears. Let's say if you search for a coffee cup, what do we see? We see lots of cup images, but we not just see cup, we also see table. And if we search for table, we rarely see a cup. So what this shows is that probability of seeing a table given a cup is much, much higher than probability of seeing a cup given a table. And we can just use this observation and apply it at scale. to tell whether an image, to find what is an object and what is a support. So we come up with an approach using this. We call this counterfactual in painting, where what we do is, this is a simple example, cat sitting on a table, and we use generative model and ask what could be a replacement for that object. Let's say if I try to replace cat, we get many different candidates, like it could be a coffee cup, it could be a vase, it could be a power plant. But if we try to replace table, we always get a support structure back, either in form of mostly a table or like. So what this shows is that if there are multiple objects, then it is highly replaceable. That's the first thing we remove. And if there is a limited variation, that's likely a support structure, and then we remove it once. But this works on most of the cases, but there are certain cases where it fails. When there are hard shadows, the model is unable to remove, because looking at the shadow, even if you try to remove it, the model thinks that something has to be added. And second failure, common observed failure that we saw, is that when there are transparent objects, because it has see-through to the background, then it fails to detect and remove them. But we want to go beyond and not just get simple object relation. We want to answer what would happen if I open this cabinet. If we ask our today's powerful generative model, either it conveniently looks away and ignores the problem, or if we ask it too nicely with the prompt, it does something magical that is physically impossible and rearranges the plate. So we want to go beyond simple support and object dependency and answer what if scenarios. What would happen if I remove the bottom bowl first, or if I remove the bottom table, if the system is going to be stable or if the system is going to collapse? This will help us probe deeper dependency beyond simple support, and it will also help us identify complex object interactions. After this, I'm more excited about probing actual physical knowledge. Earlier, I showed you this example of this simple test of gravity, where there are, of course, there are lots of other issues. But let's say if this problem goes away, in fact, we can use simple observation to improve gravity or probe gravity. So here is another example, generated. I know it's fast, let's slow it down. If you look at it, they are almost hitting at the same time. How do we probe for it? We know that when objects of different mass or different sizes they fall, they almost hit at the same point. We can use a simple observation to find whether the generation is realistic or physically plausible or not. But we have to go beyond, and we want to see how we can model collision, friction, and see if we can probe and we can recover this concept from this model. With that, I want to emphasize the broad theme. We started with intrinsic physics. We are just beginning intuitive physics, and future will be doing actual physics. This will have enormous application in robotics and beyond. And this may help us discover hidden physical knowledge inside this model. But I'd like to thank my students first, who are at the top, who have done most of the hard work, and then my mentors at the bottom. Happy to take any more questions if you have.
So it seems to me, currently you are mostly to represent an image space, right? For example, you have images that have different recognition conditions.
Right.
From some
Right.
But then it's translation from equations, physical equations to something in the image space, right? There's still some differentiation.
Right.
So just curious.
Yeah, very good question. So far, we have been dealing with mostly images because that's the model that work really well. But sooner or later, we'll have video models that are going to operate extremely well. That will allow us to do much more higher order knowledge probing inside the model, because video gives us much more signals of what's going to happen next, like what if and everything. And we can also look for certain properties like object trajectory. Does it make sense? Object motion, does it make sense or not? And then we can characterize them, what they are good at and what they are bad at. I think that will help us to refine these models in a useful way.
I guess like okay, still you have some like 3D or 3D kind of image space.
Sure.
Video, right. So, but maybe I'm not sure if it's a similar example. I want to kind of impose or cover certain physical rules to my generative models.
Right.
Fancy equations.
That's a very good question. I think one fear that I have is if we impose too many constraints to this models, the model may become too brittle or may just work on one of the domain that you are interested in. Then it may not work on other problems. the way I see this, these models are generalists, but they are very bad specialists. We want to preserve that. We want to use this general representation that these models have learned, which are good, though even though they have some problems with it. But for domain-specific problem that you are interested in, then you can build a modular or top-up approach where you can apply these rules to those instead of bottom-up retraining with physical rules. Yes.
I have a question about the feasibility of like when you're in a, this is actually a conversation we had on Twitter. When you have a video generation and you have like this 3D scene, and so you talked about like around the corner, like I add cars to it. And then with respect to like the video I'm thinking of is the open Sora, like the Sora release where like it goes through like a longer hallway in the video generator. And I'm just curious, like, because you really only evaluate like LPIPs, and so how can you maybe evaluate more of like the feasibility of?
That's a good question. Actually, we are also looking into structure from motion and code my pipeline and see if the 3D point cloud 3D reconstruction that we get is sensible or not. And we can look at reprojection error to see how 3D consistent that or not.
Yeah.
But the problem with that is slow and not scalable. The LPIPs PSNR is a scalable way to evaluate at scale, one, but we are still doing the actual 3D consistency evaluation as well. It's not that we are ignoring it, but that's a good question. Like, how do we do it at scale in an efficient manner? And I don't have an answer to it.
Okay.
Any other questions? I guess I have some question about learning physics, which is you know, to do in the future, right? So you know, people have tried to learn models to do physical simulation explicitly. So you often have some kind of abstraction, like they already know objects.
Yes.
They try to predict how object will move following physics.
Yes.
Or they have some particle-based representation.
Yes.
So I think about you know, like Sora type of video generation that follow physics law. You're thinking about getting some kind of abstraction first, and then you learn.
I agree. I like that approach. I agree with you that we need some explicit physical data or representation. The one way to get it that right now is simulation at scale. If we can recover those trajectory in object and everything, we can improve them to some. But at the end of the day, that is good way to improve some of the capabilities that are there. But at the end of the day, we want to deploy them in real world. So we want to still have data set or collection where we have this actual physical phenomena that emerges that happens in the real world scenario. So we need kind of both set of things.
I mean, data set, yes, you have real data set,
Right.
For sure. But also, you know, what we'll say, training a model that understands physics.
That's right. Of course, we need some explicit physical laws as well, or physical based learning. We need to put some learning into this model. This properties will not emerge just by looking at millions of images or billions of videos. There has to be some explicit way of understanding. Even humans understand by when someone explains them what is a gravity and everything. Okay, we do understand, we have a sense of it. But if you ask general audience like layman and ask them which of the two balls will fall fast, one is 10 kg and another is, let's say, 5 kg, and they would say that more mass will fall fast. We do understand by learning and everything, so we need some rule-based knowledge baked into this model, either in terms of symbolic representation or in terms of coming up with novel losses, or even by making some architectural changes. We'll have to do that, but first we need to make sure that we get enough juice out of whatever is available.
Right. I guess because you mentioned there's also you mentioned application robotics, right? You know, do you think you have to really generate realistic looking videos and images that follow physics law, or maybe you don't need to generate pixels at all?
So we are actually, that's a good question, and we have some ongoing work. I didn't show this, where we are trying to, and we found that it does matter the quality of videos that we make. If we are trying to imitate a robot to do the same task, here we are trying to teach a robot to do the ironing the shirt. And the quality of data set, we found out that it matters a lot. The higher the quality of the video that we have, then that's the better way to teach a robot to it. So it's still an ongoing work.
Quality data, yes, but also like when it's a generative model, right? You want to generate model as a data source. You want to use the generative model as a data source, or you want to use it for control.
we want to do both. Here we are using it as a data source, but in future we want to use generative model as the backbone for different robot downstream applications. For that, yes, I agree with you that we need to have some explicit representations to teach this modern actual physics.
Okay, we can thank the speaker again.
I don't know if there are any questions on Zoom.
No. Someone did say hi, and they are also from you.
Oh, okay. Okay.
Yeah.
Oh, thank you.
None of our meetings are.